Hey! Hello, data lovers! Welcome to a new conference of our DataXDays event. We meet every Tuesday in June at 1 p.m. and 5:30 p.m. for new data topics. Tonight, we welcome Ryan Dawson, an engineer at Seldon working on open source machine learning serving, who will explain why DevOps for machine learning is different. You can ask all your questions in the chat, and we will reserve time to answer them. Without further delay, let's welcome Ryan. Ryan, the stage is yours.
Excellent, thank you. So why is DevOps for machine learning so different? This session is going to be a bit of an introduction to the MLops landscape. And in particular, we're going to look at that MLops landscape starting from a DevOps perspective and understand why the landscape is so complex. In order to do that, we need to understand the differences between data science and programming and how those workflows differ from one another. With a better understanding of the machine learning workflow, we can then drill into more specific MLOps topics, such as, in particular, training, serving, and monitoring. So let's start by looking at the DevOps background, the landscape of DevOps. DevOps is all about supporting a smooth journey into production for applications and then monitoring those applications once they get there. So this diagram depicts that journey through a code build release kind of cycle through to monitoring and then releasing a new version. It's each of the various tools that are part of the DevOps tool stack allocated their niche within the cycle. MLOps is in a rather different place right now. There are surveys which suggest that up to 80–90% of ML projects never go live. The infrastructure around machine learning is complex. This diagram is from a famous paper, The Hidden Technical Debt in Machine Learning Systems. And the small box in the middle, the little black box, that's the machine learning code. So the authors of the paper are telling us that the effort and work involved in writing the code is small compared to all the data verification and collection and transformation work on the left, and also small in comparison to all the monitoring and serving infrastructure and work on the right. And this is reflected in the MLOps landscape. So this diagram is from the Linux Foundation for AI. And the Linux Foundation for AI here have attempted to take all of the tools within the MLOps landscape and put them into different categories. And as you can see, there's a lot of different categories and there's a lot of tools within each category. So it's a much more complex diagram than what we saw at the beginning for the DevOps landscape. But hopefully over the course of this talk, we can start to understand why there's so many categories and why there's so much complexity in the MLOps landscape. We'll understand what the source of this complexity is and how it arises and how to navigate this landscape. So why is it so different? Well, running software, if we think about it, it performs actions in response to inputs. So traditional programming codes these actions as explicit rules. Now, this is rather different with machine learning. Machine learning does not codify explicitly. Instead, rules are set indirectly by capturing patterns from data. And those patterns are then reapplied to make predictions. So machine learning is more applicable to a different kind of problem domain, especially to focused numerical problems. If we think reflecting on some examples might help to make this clearer. So traditional programming, we can think of, in particular, old terminal systems. These make this very clear because with terminal systems, you had to type in inputs specifically, and you would see outputs come out on the terminal. And we can think of a progression where when learning to program, you start with hello world, and you add more control structures. So you can have if statements with if this input, then output hello Bob, or hello Jim, or whatever, different outputs. And this is also reflected in these apps that help kids learn to code. So this screenshot here is of an app where you write code in the square at the bottom, and those instructions tell the turtle what to do. Now, if you think about data science problems, these look rather different. They're traditionally put into two categories: the classification and regression problems. Classification problems are all about putting a data point into a bucket. So, for example, it might be you're given an image and you need to recognize whether the image is of a cat or not of a cat. Regression problems are the other category, and this is about making a numerical prediction. So you might have different data points for advertising spend and type of advertising spend, different types of advertising placement, and you might want to make a prediction on what kind of sales return you can get for that spend. With machine learning, the traditional Hello World application is instead the MNIST dataset. And MNIST is a set of handwritten samples of writings of digits. And it's an image recognition problem to be able to recognize whether a written sample is of a particular number, number 1, number 2, number 3, etc. So with regression problems, the method that's used is to try and draw a line of fit through the data points. And the aim is to get the error to a minimum on the line of fit. So you want to reduce the distance that each data point has to the line. I appreciate this might be somewhat basic to much of the audience, but it's worth recapping this because it helps us to understand the fundamental differences between machine learning and traditional programming. So the line of fit is represented by an equation, and we have coefficients in the equation, which are the weights. And those weights can be adjusted to adjust the line to make it pass more smoothly between the data points, reducing the distance as far as possible. And the approach that's used to do this, the algorithm, is gradient descent. So it's not purely like random adjustments to the weighting, the weights on the equation. We go in a directed way. The details of this are not especially important for this talk. What's important is that the method is numerical, and it's also worth noting that the method is tunable. So there are different parameters that you can put into gradient descent and get slightly varying outputs. So there's an experimental aspect to the application of the method as well. This experimental aspect to machine learning is also reflected in some of the tools that data scientists use. So there's an exploratory element to it. Jupyter Notebooks, for example, are very good for exploratory work. So they let you sort of play around with different slices of data and visualize different operations on the data within the notebook. So let's now move on to comparing the kind of journey through build and deployment that you take with traditional applications versus machine learning applications. So starting with a traditional software application, this will usually start with a user story or set of user stories. To make things simple, let's assume we're making a calculator application. So we want to put numerical operations, inputs into the screen, and we want the calculator to work out the correct answers for us. So we can code this up. Here there's a Java implementation of a calculator that takes the inputs and will come up with the correct numerical outputs. We compile this application, and then we get an executable. That executable can be distributed to users, and they can then use it in a way that performs the operations that satisfy the user stories. Of course, these days, probably we won't be distributing an executable. More likely, it's going to be a web application. But the web application is also an executable. So it's essentially the same applies. Now consider the machine learning build journey. Here we start with a set of data. So we start with a data set. This data set is a very simple data set to represent years of experience and salary. there might be other data points, but if we just simplify for now and assume it's just years of experience, and we start with a question, can we estimate or benchmark employee pay from this data set? We could approach this by trying to apply we can approach it as a regression problem, and we can use linear regression on this, and we can use build a Scikitlearn model, and we train that model, and we will then be able to make a prediction for any given data point. What would the salary be in line with the data set that we've been given? And we can then supply predictions to the business. So if they asks us of a particular individual number of years of experience, we can say this is the salary based on the data set. And perhaps the business are happy with this and they use it to benchmark salaries in the department, and then they want to use it again next year, and they start up a cycle of using this data. Then our situation changes a little bit, especially if it becomes more frequent, because then what we want isn't really a prediction or set of predictions, but more like a predict function. Because we probably don't want to have to rerun the training process repeatedly every time the business want new answers. And this problem then gets magnified if there's another business unit, say another department, that wants to use the same data and gets predictions as well. Especially, there's an especially extra layer of complication here, because we don't know whether that department, the data is also applicable to that department, even if we do know that it's applicable to us. Given all this extra scale of predictions that we're looking to make, probably we're going to be interested in running the machine learning code within a web app. So maybe we add a REST API around our Python code, and we look to run it as a web application, and we package that application in a Docker container as a Docker image so that we can deploy it like we would other Docker applications. Now, this is a perfectly valid and commonly used approach, but it is just one approach to deployment. It does have some drawbacks, because you then end up Dockerizing or including in the training data in the Docker image, and resulting in a large Docker image. So it's also common to separate the model from the data. So here in this case, the regressor, the Python variable called regressor there, that's our model, and we could serialize that Python object into a file using pickling, and load that into another Python running application, provided that application has the right dependencies. And then we can run that model with just the weights, the weighted model present, the weights for that run, that scikit-learn model, and avoids having to go through the training process again or package the training data with the application. This varies a little bit from framework to framework. So I've mentioned scikit-learn there, but it will vary a little bit depending on which framework's being used, and it can change somewhat radically if it's not Python. And once we start looking at the data science machine learning journey in this way, we start to see how this landscape can be so complex. All of those different subfields that we see in the Linux Foundation for AI's MLops Landscape diagram, some of them we can start to make sense of here. So in the top left, we have tools that will be dedicated specifically to the space of data, tools dedicated to storing data and making it easy to provide manipulations on data transformations. There are also tools specifically aimed at the training space. So tools that aim to make it easier to run training processes where the training might take a long time or require lots of compute. So you might not then want to run it on your own laptop. Then you need a platform to be able to enable that. There's also tools that are dedicated to tracking. So when you're running these long-running training jobs, you also want to be able to track exactly what operations have happened at what points, and what the changes were to the data, so that you have a history of the changes on the data, and you feasibly know how to be able to go back to previous versions or retry steps. There are also tools in the space specifically of making batch predictions. So for that use case where the business want predictions, say, every month, and then you don't necessarily want the model to be running on demand all the time. You might then only want to start it up and make it available at the point when the predictions are needed. And there are tools in the serving landscape as well. So these tools that will help add a REST API around the model and make it available for real-time predictions. Some of these come or are coupled to specific frameworks, and there's others that are more general. There's one in particular here. Selden is the open source serving solution that I work on. At Selden, we also collaborate on another one called KF Serving, both of which are part of the Kubeflow ecosystem. Kubeflow being a open source end-to-end solution for Kubernetes. So there's another space of tools which are aiming to be end-to-end and provide more of a platform with all of the different elements included within the platform. Often the end-to-end solutions have a certain bias towards particular parts of the journey. So machine learning is different. The key points to take from what we just learned about the journey here are that training data and code together drive that fitting process. It's not just the code. Whereas in a traditional DevOps process, you would essentially be just looking at the code. The closest thing to an executable is a trained or weighted model, which varies a little bit with Toolkit. There are also circumstances where retraining can be necessary. So if you think in particular of in the fashion industry, where the nature of what you're selling is seasonal, then if you're making recommendations, say, that using a model that's been trained in winter, you're going to be recommending coats, and in the summer, that wouldn't really be applicable. People they're going to be wanting summer wear rather than coats. It's also worth noting that there's this training process can involve very large volumes of data, and that means long-running jobs and lots of resource. So we can now drill into this in more detail and see more of how the landscape works by looking at the workflows in more detail. So a traditional development workflow would start with a user story, then we write some code, probably submit a pull request. Hopefully the tests will run automatically because we've got a DevOps set up. Then when that's reviewed and merged, then a new version will build. That new executable will be deployed to a test environment where further tests will be run. It can be promoted to the next environment and so on. When it reaches production, then we have monitoring. And the monitoring will mostly focus on looking for stack traces and error codes. We'll be looking for something very distinctly going wrong with the application. Most likely Docker will be used as the packaging, and the driver for the automation, the DevOps automation, will be a code change that can be detected in Git. Now, with machine learning workflows, the driver might be a code change, or it could be new data. And the data is not necessarily in Git. Git's not a great data store for data in large volumes. Once you get into the gigabytes, it doesn't stand up quite so well. The workflow is more experimental for data science. It's based around taking slices of data and playing around with those and looking for patterns in that data. And when it comes to getting to production, what you're looking for is not just errors in the application, but you'll be most likely or very often looking for quantifiable performance. So you're looking at the quality of the predictions that the model is making. There can also be use cases where the model is learning further, like this updates to its weights through every prediction. But to simplify, let's just look at offline learning, so where the training is done separately from the deployment or prior to deployment. So now let's consider a typical machine learning end-to-end workflow or representative. So there'll be large data inputs or training data, and just to simplify, let's kind of skip ahead a little bit and assume that it's been pre-processed. So any cleaning and transformation that's needed on that data has already been done. The data scientist is going to try stuff out locally with a slice, look for some patterns that they can use. Then they're probably going to graduate to trying stuff with larger volumes of data, running long-running experiments in some hosted environment. There'll be collaboration with other data scientists, often using Jupyter notebooks and probably storing those in Git. Any models produced may well be serialized and pickled with Python models. And the models can then be integrated into a running app, perhaps by adding a REST API, by serving the model using a serving solution. And any app that's consuming the model, so we assume that if we're serving it properly, it's going to be part of some wider application that needs to make use of these predictions. That app, we'd have to integration test to make sure that the two parts work together, that it can consume the machine learning predictions correctly. And then when we roll out this model, we would monitor the performance of the model, looking for specific metrics. And the metrics, I should say, they can be kind of custom to the use case. But let's drill a little bit into metrics now and understand a bit more about the metric space. So if we consider a metrics example, say we have an online store. And with online stores and e-commerce, it's very common to use A/B testing as a method of rolling out new versions of models. So let's say that we're making recommendations to potential customers to buy certain products, and we've got some variations on our running model. We've got the running version that's called the control, and then we've got other versions called variation A and B here. And we split the traffic between those versions. So most of the traffic will go to the control, but a subset of the traffic will go to A and B. And we'll run that splitting process for a while until we've got a statistically significant sample. And in this case, we can say that variation A has the best conversion rate. So a higher proportion of those recommendations lead to sales. And that's a useful metric, but it may not be the only metric. These cases can get complex. So it might turn out that we are recommending through this model products which are quite controversial. So some of our potential customers really like those products and buy them, and that increases the conversion rate. But some customers might actually be really put off by these recommendations and go to a different website and close our website. So there are trade-offs to consider, and you might want to monitor for more than one metric depending on the use case. So this is complex. It's a complex landscape, and I think we're seeing the challenges here. And added complexity or the problem is enhanced by the fact that in many organizations, these different concerns are rather siloed. So you might have the data scientists dealing with just their specific part of the process, and then it's sort of expected that they'll be able to hand over their work to a traditional DevOps team. And without the proper context, the traditional DevOps team is going to look at the Jupyter notebooks or whatever that's been produced by the data scientist, and without that context, they're likely to just be very confused and be like, "What is this?" Whereas in a more mature setup, you might have a different breakdown of the workflow. So in this case, we have a whole different role here at the beginning. We have data engineers who deal with obtaining the data, transforming the data, cleaning it, getting it to the right state for data scientists to be able to work with. There'll be an understood handoff between the data engineers and the data scientists. and the data scientists can then build the models and take those models and again bring to another understood handoff to the ML engineers. And this, in a more mature setup, then would be essentially still a DevOps team, but more of a DevOps team that knows about the particular context of this machine learning application and knows how to be able to then run that in production. So this is new territory. There are special challenges for machine learning that are unfamiliar from a traditional DevOps perspective, at least right now. But at least now we have a bit of a grounding in what those differences are. We can now drill into some of the specific subdomains and understand those in a bit better. So we can now dive into training. We'll start with training at least. We'll see a bit more about how slices of data are used to train models. And then we'll go into serving, and then we'll see how serving links to rollout and monitoring. So starting with training, there are tools available in this space, as I've mentioned before already. So we mentioned Kubeflow, and Kubeflow has a particular tool within its ecosystem, Pipelines. And then there's other tools such as MLflow and Polyaxon, which have a quick look at. And these are about providing facilities to run long-running training jobs that need a lot of compute power on a hosted environment. And typically that means creating some sort of manifest that specifies which steps are to be done in which order. So there'll be steps such as cleaning the data and then performing further transformations. And those will be done in a order. In fact, we can think about this order using this diagram. So in this case, we have a pipeline where data is downloaded from some source. It's split so that different parts of the data set can be used for its particular purposes within the training process. And then there can be an evaluation done on the training once the model is trained, using metrics that are collected as part of that training to see how well that model might feasibly work. So I mentioned that Kubeflow has a pipelines subcomponent, and here is a screenshot from the Kubeflow dashboard, and pipelines is highlighted there. There are other components within Kubeflow, but we're not going to go into those here. And so with pipelines, you can run these parameterized experiments. So the box on the left here shows the inputs to an experiment run. So prior to doing this, probably a pipeline would have been uploaded. So you create a manifest for what the operations are and which order. And you'll be able to do a run. And you could create multiple runs and even run them in parallel if you want, with different parameters to see which parameters result in the best performing models, at least given the data that you can evaluate it against. And for any running any run that's in progress, there'll be a screen such as on the right where you can drill into the run, and each operation is executed as an individual container, and you can access the logs for each container and see how it's doing and monitor the progress. MLflow has a similar concept where you can create runs with different parameters and export the data once it's completed and so on. So from a traditional DevOps perspective, these training platforms look quite similar to CI systems like Jenkins, but they're also rather different. They're different in that when you perform different runs with different parameters, you're kind of playing with different options to see which was going to result in the best model. But that means you then have to have a definition of which is good, which is the best model, and then you have to make a choice from that. Whereas traditionally with continuous integration, you normally just build continuously, and whichever, as long as the build is successful, then it goes through. But that's not to say, as I say, there are similarities between these training platforms and CI, and sometimes the training platforms have integrations available to CI systems. So let's say we've managed to set up such an integration, and we've got a way of building our model, and we want to be able to serve it. So we want to put an HTTP REST API around the model, and we may use a serving solution. There's a range of those available. I've mentioned Selden, which is the one I work on. There's also some like TensorFlow serving that's specific to TensorFlow, or SageMaker, which has some serving capabilities, but is specific to Amazon. And often these serving solutions have the idea of packaging the model and hosting it, perhaps in a storage bucket or some disk location, so that the serving solution can then obtain that model and run it. And serving solutions often also come with support for rollout and some support for monitoring as well. So here's an example manifest for serving with Selden. And this is intended for Kubernetes. So this is a Kubernetes custom resource. And here the model URI element contains a value that points to a Google storage bucket that contains a serialized model. I've put an image from the bucket at the bottom. And we also need to tell Selden here that the model is a Scikit-Learn model, so that it knows to serve it as a Scikit-Learn model. There are also options with Selden to run models using Docker, and that's a perfectly valid option. I'm just using or primarily using the serialized model here as an example, because that's quite different from DevOps. So it's a different kind of concern that has to be handled. And as I mentioned, the serving stage links into rollout and monitoring. So if we drill now a bit more into rollout, there are different rollout strategies, one of which we've talked about a little bit already, which is the A/B test, where the traffic to the model is split between different versions, and each version gets a certain percentage, and you monitor that over a period of time until you've got a good enough sample. There's a more simple rollout strategy that's related called the canary, where just a small percentage of the traffic is allocated to a new version, but there'll just be one new version, and typically over a shorter period of time. And the monitoring probably won't be quite so detailed. It'll mostly be doing some sort of sanity checks to make sure that the new version is okay before deciding to promote the canary to become the new default version. The other strategy is shadowing. And with shadowing, all of the traffic goes to both the new and the old model. But it's only the old live model's responses that are used and that go back to the consumer. With the case of the shadow, the actual shadow version, its responses are just kept. Like they don't go back to the consumer. Often the reason for doing this is so that you can monitor the shadow and compare it against the live version. So you might then want to be storing those responses for comparison, or at least doing some aggregation on. So as I said, serving solutions have some support for these kind of strategies. And with here's a canary example with Selden. This supports the traffic splitting between the default and the canary models. And each of them has a separate section in the manifest. And there's also an option with Selden to do A/B tests. And here the control and the variant have their own sections in the manifest. And we're also setting here a traffic percentage. So we're going to control exactly how much of the traffic goes to each of those options. Because the rollout process is bound up with metrics, and that feeds into monitoring, there's integration available in Selden for Prometheus and Grafana, some of the most popular kind of open source monitoring solutions on the Kubernetes stack. And basic metrics are available out of the box. So the serving solution can tell what the latency is and what the frequency of requests is. More complex metrics, as I was discussing, say, in the online store use case, they tend to require a bit of custom work to expose those particular metrics. There are defined interfaces, but it's because it's specific to the use case. There needs to be some work on the model and its wrapping to be able to define those outputs. And I mentioned earlier that in the shadow use case, you might want to be recording all of the predictions that the shadow is making. This kind of request logging feature is also sometimes needed in machine learning. There are other use cases as well, say where you're working in a very high compliance-heavy industry. So the auditor might require to know about every request. What was the prediction that was made? What was the recommendation that was offered by the model? Doing this then allows you to go back over all of those predictions and make comparisons and human review. And as I mentioned, it's also particularly important in that kind of shadowing use case. So you might then be able to run queries against the data and compare how successful the shadow was compared to the live model. The integration that's available in Selden is to the Elasticsearch to store all of these requests and responses, so they're correlated for querying. There are also more advanced topics within the serving space. So you get, for example, real-time inference graphs. We can think of this as, say, needing feature transformations. So if there's a transformation or cleaning type steps that are to be done on the data before making a prediction, that can be done in a separate step within the prediction graph. And that step could then be reusable on other models, for example. Or it also, once you have the idea of a prediction graph, you have extra options. So you can add components, say, to detect whether a particular data point is an outlier. And this can be important because often outliers are not within the main flow of the data. So they tend to get lower quality predictions on them. These concerns also feed into governance for machine learning. So there are bigger questions for the industry, particularly, say, in high compliance
5 minutes remaining
areas, where you might want to aim for explainability, to be able to say, why did the model make a particular prediction in a particular circumstance? And to do that, you also need provenance. So you need to be able to record all of those predictions. But you also need to be able to tie your explainability techniques to the particular version of the model that was running at the time that prediction is made. So there are ways to do explainability without necessarily having the full provenance, but provenance can also be a concern more generally for compliance use cases, to be able to say which was the version was running at this point in time, and what training data was it trained on, who was it that initiated the training run, what were the parameters on the training run, for example. And this all feeds into a kind of a more general discussion about bias as well. You have a better chance of being able to identify bias if you can understand why the model is making predictions in particular cases, which particular features it was in the training data that made most contribution to the data. As I say, these are advanced topics, but they add some more sort to the detail of the complex MLops landscape. And you can see, hopefully we can see now where they fit in within the kind of journey. So as I say, MLops is a new terrain. The workflows in machine learning are more exploratory and data-driven, and this makes them quite different from traditional DevOps workflows. MLops enables these machine learning workflows, and with a particular concern on providing, say, experiments and training processes that are very data and compute intensive. It needs to be able to provide facilities for tracking artifacts through that journey. There's another subfield is the rollout, to be able to bring these produced models into production and monitoring of those models within the production environment. Yeah, so that's my perspective, at least on the MLOps field as it stands right now. Thanks very much for listening.
I don't know if you can hear me, Ryan.
Yes, I can.
Okay, perfect. Thank you for this clear and well-explained talk and sharing your perspective. We have a question from someone, F123456, this is his login, saying, are there strategies for versioning data and generated models together?
Yes, certainly there are tools within that space. So I know Pachyderm is one of the tools that's prominent within that space of having a particular concern around versioning the data and tracking the changes on the data during the training process. But there's also, I guess there's others. It's the Linux Foundation for AI landscape diagram. We'll have them alongside Pachyderm on there.
Okay, thank you. Because yeah, you named some tools, and it was also another question. What are some tools, even open source ones, for revision control? So you named one. Well, I don't have further questions. I think it was sufficiently clear and well explained. Thank you again, Ryan. Really, thank you for this talk. I hope you enjoyed it as much as we enjoyed it too. Thanks also to our data lovers. Please don't forget to leave us your opinion using the link shared on our YouTube's chat. You have 2 links to forms, to Google Forms. If you can please fill it for sharing your opinion. And if you're just joining us and if you missed this presentation, please find the replay on our YouTube channel. Well, I will switch into French because our next session will be in French. Nous nous retrouverons à 18h30 pour notre prochain talk. Le lien vous a été envoyé sur le chat. Si vous nous rejoignez à l'instant, vous avez manqué la présentation de Ryan Dawson, mais vous pouvez la retrouver en replay sur notre chaîne YouTube. Je vous dis à tout à l'heure.
Thank you. Thank you very much.